Problem number 21. Smooth ring of radius r and mass m lies on a frictionless surface. A point mass also of mass m is placed just inside the ring and given a speed v tangent to the inner surface of the ring. How long does it take for the point mass to return to its initial position relative to the ring? Solution for problem number 21. The masses are undergoing small elastic collisions. During an elastic collision, the magnitude of the relative velocities between the masses are conserved. So the tangential velocity of the mass m relative to the ring is always v. Thus, the time is 2 pi r over v, which is answer C, and that was solution for problem number 21. Problem number 22. Two springs with different spring constants are connected in three ways as shown. In the second case, the springs are connected to opposite ends of a string, which runs under a massless frictionless pulley. In each case, the two springs act like a single spring with an effective spring constant Ka, Kb or Kc. Which of the following is correct? Solution for problem number 22. Let the springs have spring constants K1 and K2. In the first case, the forces of the springs simply add. So we have F equal F1 plus F2, which is equal to K1 delta L plus K2 delta L, which is equal to K1 plus K2 delta L, or effective spring constant Ka equal K1 plus K2. In the third case, we have same force applied to both strings, so we have force F equal K1 delta L1 or equal to K2 delta L2, and then from here we can find what is delta L1 and delta L2. We have to summarize them to find what is total dl, and after that dl equal to F multiplied by 1 over K1 plus 1 over K2. It means that Kc equal K1 K2 over K1 plus K2. The second case is not more common, but it's similar to the third case, because here we have the same force acting on each spring, but now they are connected more like in parallel. So it means that if we apply to each string force F, we have resulting forces 2F, and also enlargement dl1 and dl2 now distributed twice. So it means that we have to take dl over 2 compared to the third case. So it means that we have force twice greater than in third case, and enlargement twice less than in third case. So totally we have Kb equal 4 times Kc, or 4 K1 K2 over K1 plus K2. So it means that we have Kb greater than Kc, but Ka greater than Kb, because mean arithmetic greater than mean geometric. Correct answer is A. That was solution for problem number 22. Problem number 23. An astronomer on Earth which is a distance LE from the Sun, observes a star and galaxy. The star is a distance LS much greater than LE away, and the galaxy is much further away than the star. Throughout the year, the angular distance between the star and the galaxy appears to vary, reaching a minimum of 2 astroseconds on January 1st and a maximum of 2.5 astroseconds on July 1st. 1 degree is equal to 3,600 astroseconds. Assume the Sun, star and galaxy do not move relative to each other, and that the Earth's orbit lies within their plane. What is the ratio LS over LE? Solution for problem number 23. The change in apparent position of the star is due to parallax. Using the small angle approximation, we have delta theta equal 2LE over LS, where delta theta equal a difference between 2.5 and 2 astroseconds, which is 0.5 astroseconds, which is 1 degree over 7,200, or about 2.4 multiplied by 10 power negative 6 radians. Solving this ratio, we have LS over LE equal approximately 8 multiplied by 10 power 5, which is answer D, and that was solution for problem number 23. Problem number 24. A very heavy plate continuously moves up and down with a small speed v, switching directions after each time t. At a random time, a ball is dropped from rest far above the plate, then bounces elastically off of it. How does the ball's speed change during this collision? Solution for problem number 24. Solution for problem number 24. Suppose that our plate moving from position 1 to position 2. It has the same probability to move from position 1 to position 2 and from position 2 to position 1. So let's see what happened when the ball reaches position 1. In that moment, if a plate has position somewhere between 1 and 3, this ball will reach this plate during time when it's going down. And when plate is going from position 3 to position 2, still down, this ball has no time to reach it. So it means that during time when plate going from position 3 to position 2 and from position 2 to position 1, still our ball will collide with the plate when the plate is going up. So it means that probability to collide with this plate when it's going up greater than probability when plate going from position 1 to position 3 down. Means that correct answer is D. The ball is more likely to speed up than it slow down. This is the sample model for how a gas heats up in a container with hot walls, or more exotically the Fermi acceleration mechanism for cosmic rays. That was a solution for problem number 24. Problem number 25. A skier slides from rest along a frictionless slope with the incline angle theta equal 30 degrees for 150 meters. Then smoothly transitions into a horizontal jumping ramp of height HR equal 5 meters. Neglecting air resistance after the skier leaves the ramp, about how far will we travel horizontally before landing. Solution for problem number 25. Upon leaving the ramp, the skier has a speed v equal square root from gd. From there, the skier travels a horizontal distance x equal vt, where t is the time of flight. To find this time, it's better to use a coordinate system where x direction is along this slope and y direction is perpendicular to this slope. So now we have in this coordinate system, initial vertical speed is v multiplied by sine theta, or square root from gd over 2. Also we have downward acceleration equal to g cosine theta, which is g square root from 3 over 2. And the initial height is hr cosine theta, which is hr multiplied by square root from 3 over 2. Now we have to solve quadratic equation as usual. So we have final height equals 0, and that's equal initial height plus initial vertical speed multiplied by time minus downward acceleration multiplied by t squared over 2. And the time will be positive root of this quadratic equation, which is this one. And the last step is to find what is total horizontal distance. That will be v multiplied by t, which is about 181 meters. That's answer C, and that was solution for problem number 25.